I used to think this was about as hard as IB chemistry calculations got. Alright, so the first example, what's the concentration of ethanoic acid in that buffer there? Well, ethanoic acid's a weak acid, it dissociates, so there's the equation for that. And a salt is sodium ethanoate, and that fully dissociates, so I'm going to just have a one-way arrow for that. Ethanoic acid, of course, is in equilibrium. So Ka, well, that's products divided by reactants for the one that's in equilibrium. And I'm going to assume that the concentration of H plus at the bottom is negligible. That means it's small. No, it doesn't. It means it's small compared to the concentration of ethanoic acid. So from the data booklet, pKa is 4.76 for ethanoic acid. So Ka is 10 to the minus 4.76. That's one number. Another number I can get from the pH, the H plus concentration is 10 to the minus 5.2. That number comes from the question. Now I've got two sources for the ethanoate ion. I'm going to ignore the one from the top equation because it's only a weak acid. It's not going to be much ethanoate from that equation. The salt is going to 100% dissociate, and that's where almost all of the ethanoate's coming from. So I'm going to assume that my ethanoate ion concentration is from that salt. If you can't remember these tricky assumptions, just say that you assume STP, and the IB might let you get away with it. Alrighty, so the concentration is moles over volume, and I haven't got the moles, but I've got the mass and the molar mass. That's great. That's moles anyway, isn't it? That big fat slash is divide, 15 divided by 82, and my volume converted to decimeters cubed is 0.14. That leaves the concentration of ethanoic acid at the bottom as the unknown. I have the other three numbers. Alright, let's tidy this up. Quickly write it out again. And so by using simple algebra, and I'm ignoring sig-fig rules here, oof, that'll take me forever to do all those, I get 0.474 molar as my answer for ethanoic acid. Next question. So this one is about a basic buffer. So let's write out the Kb equation. And I'm going to assume the OH minus concentration is negligible compared to the ammonium hydroxide concentration, which means I'm going to ignore it by erasing it, just like this. Easy. So now, the ammonium ion is produced by the salt of the weak base, and we're going to assume negligible from the weak base. And my ammonium hydroxide, well, that's going to give me the number at the bottom. Essentially, the number at the bottom is the number on the bottle, normally. Kb, I'm going to get from the data booklet, well, that's pKb. So Kb is 10 to the minus 4.75. And I'm just going to pop the numbers in there. Have you spotted the teeny tiny trick that I've tried to play on you? Yes. OH minus concentration, well, that's just straightforward algebra. And POH, yeah, but I've asked for pH. So don't forget, take that off of 14. That gives you 9.6 for pH. Not that much of a trick. You've also done that the hard way. There is an easier way to do it. If you can remember this equation, there's one for acids as well, but the Henderson-Hasselbalch equation makes this quicker if you can be bothered to learn it. And you can just pop the numbers straight in without working out the negative logs or the 10 to the minus whatever. You can just use the numbers straight from the data booklet. And that gives me POH again. Well, this question is really hard the first time you look at it, but once you've seen one of them, you'll get into the swing of it. It looks like it's a trick. A strong base and a weak acid, that doesn't make a buffer, does it? Well, you know, if the weak acid's in excess, it will react to form a salt of a weak acid, and you've got excess weak acid. That's a buffer. So let's write out the equation. The IB are generous. They only expect you to do it with monoprotic acids. And so you can see I make the salt of a weak acid, and hopefully the weak reactant will be in excess, and then you know you've done it right. So let's work out the moles just to see if that's true. So moles is concentration times volume, and you can get those numbers from the question. 0.06 moles, okay? And now let's work it out for the weak acid, and hopefully that will be more moles, be excess. Then you know you're on the right track. Taking the numbers from the question, that gives you 0.2 moles, yes, that's excess. So when you do the reaction, there'll be a salt of a weak acid and a weak acid present at the end. Let's work out how many moles of the salt of the weak acid. Well, 0.06 moles. Tidy it up a little bit. So let's write out Ka, which is again products over reactants for the acid. Ignoring the H+, it's small compared to the concentration of the acid. Data booklet gives me pKa, which I can easily convert to Ka. And here's a little trick, is you can't just say the concentration of the acid is half a molar. Some of it's reacted. So do moles over volume. Now how many have I got remaining moles? 0.2 minus 0.06. That's how many moles I have at the end. And divide that by 0.5 decimeter cubed. Converting the milliliters to decimeters cubed, of course. How did I get the 0.5 decimeters cubed? Well, that's the total volume. And now we need to perform a similar calculation to work out the concentration of the ethanoate ion. So I've got 0.06 moles of that made at the end, and divide it by the total volume. And there again, you're assuming that all of the ethanoate comes from the salt and none is coming from the weak acid. That's an assumption. So let's write this out again, just make it a bit tidier. So pKa turned into Ka. Not forgetting to turn it into a concentration. Lovely. That leaves us with a concentration of H plus of 4.1 times 10 to the minus 5. pH is negative log H plus. Okay, so the pH is 4.4. No units.